In the section of our notes, we're going to be talking about osmosis, specifically just the movement of water. And we have to maintain certain concentrations of water and solute in our body, because if we don't, it can affect the movement of water either into our cells or out of our cells, which can lead to cell death. So it's really important that we can maintain that or maintain homeostasis in regards to the amount of water that we have in our system. Now, we've already talked a little bit about molecules moving from an area of high concentration to an area of low concentration. So sometimes if I give you a diagram that looks like this, and we've got two solutions, so I'm going to put, we have solution A over here, so solution A, and then on this side, this is solution B, and again, they're separated by a barrier. If I asked you to predict which way water is going to move, then you would use this rule, because I'm just giving you water percents. And this is a high concentration of water, so let's indicate high concentration of water. To this side, or to the solution, there's a lower concentration of water. So the water molecules, which are these small dots in this case, would go this way. We would have a net flow of water. So let's indicate that arrow is the movement of water, okay? Now, you might think some of the solutes would come back this way, but here's an issue that we often have with our cell membranes. Is water can flow through an aquaporin. It's like a channel, and it can go in both directions. There's no restriction of water moving. It's just got a channel and it goes into the cell and out of the cell. But the solutes, most of the solutes are polar, they have charges, and they can't cross the membrane. And the solutes and the concentration of solutes that we have in the cell or out of the cell can affect water moving in, because water can be pulled in by those solutes, okay? So if I give you water concentration, then you can remember what we've already talked about is all molecules move from an area of high concentration to an area of low concentrations of water. So high concentrations of water to areas of low concentration of water. So when we look at a diagram that's like this, and I've got two solutions, and they're separated by, this is a plastic membrane, and it's showing you here's the plastic membrane. Here's the solution in the bag. Here's the solution that's in this beaker. So here's the beaker and here's the bag. So when you look, you can see that there is more water molecules over here, a higher concentration. There is less water molecules on this side. So we would be able to predict that we're going to have a net flow of water out of the bag and into the beaker. So we would see a net flow of water out, and this bag would shrink up and have less water in it over time and less mass. Now, sometimes I won't give you percents of water or show you a diagram and you can see where there is a higher concentration of water versus a lower. And I might say something like a cell was placed in a hypertonic solution. So in situations like this, you're going to have to remember another rule. So this is like rule number 2 here, is that water always moves from a hypotonic solution to a hypertonic solution. To help you remember that, I want you to think about, like, if you go to a friend's house and they have a bunch of people over, everyone's hyper and having a good time, that's the party that you're going to want to go to. So you might remember, we're going to go to the hyper party. Okay? And so water is going to go to the hyper party. It's going to go to the hypertonic solution. Okay? Now remember, in a solution, we have two things. We have the dissolved molecules, which are the solutes, and water is the solvent. Okay, so up here, we would have the solute is what's getting dissolved. And then this is water, it's the solvent, okay? In a hypertonic solution, or the reason why we say that solution is hypertonic is because it's a solution that has a higher amount of solutes or a higher concentration of solutes in it compared to another. The hypotonic solution is the one that has the lower concentration of solutes. So that would be an example if, like, I put a cup of sugar in Kool-Aid, and then in a different batch, I only put half a cup of sugar in Kool-Aid. The one that had the full cup in it would be hypertonic. It has more solutes in it, more dissolved sugars. So anything that is not water is a solute. So even oxygen can dissolve in water. Oxygen's a solute. CO2 is a solute. And then the Kool-Aid that only had the half a cup of sugar would be the hypotonic solution. Now, if I put the same amount of sugar in both of them, then we have two isotonic solutions. So solutions that have the same concentration of solutes in them would be isotonic. You might remember an isosceles triangle is a triangle that has two equal sides. And so iso equals two equal. So here's some different questions that we can have. So we see that we have here's a solution in the bag. And so I'm just going to put solution, let's call it A, and then out here is solution B in the beaker. So this bag is floating in a solution, and the bag also has a solution in it. It says the beaker is hypertonic. So this solution is hypertonic compared to the bag. So that means that there's more solutes out here in the beaker. It's the hypertonic solution. And water is going to go from the hypo to the hyper. Water is going to come out of that bag in this situation because the outside, this part, is hypertonic, and water goes to the hypertonic solution. Here we have a cell membrane. This is cytoplasm with some solutes in it. And remember, cytoplasm is mostly water, but it does contain dissolved molecules, and those are the solutes. If we have a solution outside of the cells, which has more solutes in it, then that outside's hyper, which means that the inside is a hypotonic solution. Water's going to go to the hyper party just like you would go to the hyper party. So the water would move out of the cell in this condition, and this cell will shrink up. If it loses too much water, the cell's going to die. Let's go over here, and if we put a cell in a hypotonic solution, we can have cell death as well. If the outside is a hypotonic solution, then that means the inside of the cell is a hypertonic solution. Water will go where it is, or into a hypertonic solution. If too much water goes in, just like if too much water goes into a balloon, then your cell is going to burst and it's going to die. In an isotonic solution, there is no net movement in either direction. So that means that we have a pretty equal exchange of water. Water's still going to move, but if some water moves in and we get more water inside, that means some is going to move right back out. And our cells aren't going to expand and they're not going to swell. And so this is the ideal for our cells because we don't want them to swell. We don't want them to shrink. Now, if you say a solution is hypertonic, I don't want you to think that it's always hypertonic. It really just depends on what you are comparing it to. So for example, if you say I'm short, well, that depends. I might be short to some of you students, but if I go to kindergarten, then I'm going to be tall, okay? So you can't keep that label on me. It just depends on what you are comparing to. So if I have a beaker of pure water and one that has a little bit of sugar in it, then this sugar solution would be the hypertonic solution compared to the water. It would be hypo, okay? Now, new scenario, I'm going to take that 3% sugar solution and I'm going to compare it to a 10% sugar solution. Well, now that 3% sugar solution is the hypotonic solution because it has less solutes in it than a 10% sugar solution. It would be the hyper one, a hypertonic solution. Now, you probably heard the old wives' tale that if you give kids a bunch of sugar, that's going to make them hyper. That's actually not true, but it is kind of a good way to help you remember that hypertonic is going to be the solution that has more dissolved stuff. So like more sugars, more oxygen, more CO2, that's going to be the hypertonic one. So more solutes, that's going to be the hypertonic solution. Sometimes though, I'm not going to give you water amounts. I'm not going to tell you which solution is hypertonic. I'm just going to give you solutions, and I'm just going to give you the amount of solutes we've added. So we've added 0.8 moles of glucose in this solution, and we've added 0.4 moles of NaCl. This is just a unit of measurement, okay? It's actually a concentration. Now, here we have, this is called a U-tube. And I've got two solutions, one on each side. And since I'm just giving you the amount of solutes in the solution, you're going to have to remember a third rule because I'm not giving you water amounts. So you can't, we're going to predict which way water's going to go, but I'm not giving you water. So you can't predict that. You can't use high concentrations of water, low concentrations of water. You could use hypertonic and hypotonic, but this is the easiest way to answer this question. Just remember solutes suck water. Okay, wherever there's more solutes, that is the direction that water will flow. So here's a semi-permeable membrane, only water can cross. And if you look here, if I add this up, this is 1.2 moles of solute over here, because those are all solutes. Over here, if I add that up, it's 0.9 moles of solutes. 1.2 is a higher amount of solutes, and solutes suck. So the water would move in this direction. Solutes can't move. They're stuck on this side, but water would move. And what's kind of weird about this is the water level will go up over here, and it's going to go down over here, and it looks like it's defying gravity. But it's because the water is moving to where there's more solutes. Got to pause for a second. Now, on this next example, we can use all three of those rules. We can look at this and try to figure out where there's a higher concentration of water and a lower concentration of water to figure out which way water is going to move. Because remember, this is osmosis. We're not moving any solutes. When the solutes can't cross membranes, but water can, then we're going to predict which way water is going to move. We could remember water goes to the hypertonic solution, or the hyper party, remember. Or you can remember that solutes suck. Wherever there's more solutes, that's where water is going to go, okay? So in this situation right here, this one's pretty easy. If I show you that here's my solutes over here, there's none over here, solutes suck water. So some of these water molecules, we're going to have a net flow of water moving over to this side. And you would actually then see that this would go up higher. You would have an increase in water. It would actually move up a little bit if this was a barrier that's only permeable to water. And this level would go down on that side of that barrier, on that side of the membrane. Okay. You also could have done, it's 100% water over here. When we draw solutions, it's really nice if we just draw 10 molecules total, because then all I have to do is look at 1, 2, 3, 4. There's 4 out of 10 molecules. 4 divided by 10 is 0.4. When we times by 100%, okay, that will then give us 40%. This is a 40%, or just 4 out of 10. That's 40%. 5 out of 10, 50%. 2 out of 10, 20%. So it's 100% water over here. It's 40% water over here. Water moves from an area of high concentration to an area of low concentration. Or you could have noted like, okay, well, all the sugar's over here. There's none over here. This is the hypertonic solution over here. This solution over here would have been the hypotonic solution. And water is going to go to the hypertonic solution. Like you're going to go to the hyper party. A few more examples. We've got salt is the solute, and on this one, I would just use solutes suck. Wherever there's more solutes, that's where the water is going to go. So water would move out of that cell. It says that we have, it says a hypertonic environment. And if you look here, we've got way more solutes on the outside compared to the inside. So these water molecules are moving out. That's kind of what it's showing you in this diagram, is we would have a large movement of water out of that cell, and that cell is going to shrink. If we have two solutions that are isotonic, though, remember, water is going to move. I'm not going to show that moving because it looks like I'm making the solute move. Water molecules are going to move, not the solutes. They can't. It's not permeable to most solutes. But we're going to get an even rate of exchange. And then over here, we've got solutes in, no solutes outside. So the water is going to go solutes suck. It's going to go into that bag or that cell that's in that outside solution. All right, we were looking at solutions and we were looking at membranes, but like more like plastic membranes. Let's take a look at cells and what's going to happen if solutes aren't moving through the membrane, but water can. So cells are greatly affected by what type of solution they're in. It can be a hypertonic solution, a hypotonic solution, or cells can be put in isotonic solutions or be surrounded by those types of solutions. And so we have to make sure that the solutions around our cells have the right amount of solutes and the right amount of water. And so you're always trying to maintain homeostasis when it comes to the amount of water and solutes that are in your body, okay? Too much water going into our cells, too much water coming out, and it can lead to cell death. Now, a couple ways that you can remember what's going to happen to cells if you place them in the different solutions. So notice I wrote hypotonic and a hypertonic solution. So a hypotonic solution will make cells swell. So I like to think of that hypo. So if you take a cell and you drop it in a hypotonic solution, the cell is going to swell up with water, okay? If you take a cell and you put it in a hypertonic solution, think of that E as being kind of like a shriveled up, wrinkly O. Cells are going to shrink. So that's one way to help you remember what would happen to cells if we put them in different solutions. But again, you can just apply rule number 2, is that water always goes to the the hypertonic solution. Now, in a diagram like this, what it's telling you, if it says that there's a hypotonic solution, right now they're talking about outside of the cell. If the outside of the cell is a hypotonic solution, then that means that the cell solution, that cytoplasm, which is water and solutes, is hyper. In comparison, water goes in, our cells can burst. We need our cells to always be in a solution that is isotonic compared to our cells. So there's no net movement of water in or out, causing our cells to shrink or swell and burst. If our cells are surrounded by a hypertonic solution, so we have a hypertonic solution outside is what this is indicating. The inside of the cell must be hypotonic. Water goes to the hypertonic solution. It would come out and our cells would shrivel up. Now, we have names for these conditions when our cells swell and burst or if they're shriveling up and not able to function. So when our cells swell and burst, we say that is called cytolysis. Cyto means cell. Lysis means to cut or break. So our cell membrane is breaking. So it's cytolysis. This is going to be cell death. When our cells shrink up, it's called crenation. To help you remember that, if you think of cremation, like if something is cremated, it's going to be much smaller. So like, for example, if a pet is cremated, like you can save their ashes and put it in an urn. And so it's in this little urn or this vase-like container, much smaller. So crenation, think cremation. If something's cremated or burned, that ash is going to be much smaller when it's over, okay? I do have that written here for you. So animal cells bursting and dying is called crenation, I have that backwards, so I need to change this. Let's go ahead and just cross through this like this. So animal cells bursting and dying is cytolysis. When they shrink, it is called crenation. Okay? Now, plant cells can't burst because they have a cell wall. So water will go in and the cell membrane will expand, but it'll eventually hit that wall. Pressure will build up and then no more water will be able to go in. And this is a really tight plant cell that's full of water. Okay. And we're going to talk about, this is actually what plants need. Plants their cells need to be given or surrounded by a hypotonic solution. So that's going to make our plant cells real tight. We'll talk about, again, why that's important. If we put an isotonic solution on our cells, then some water will go in, but some water is going to go out. And we're going to get a little bit of a squishy plant cell here because we don't get a lot of pressure buildup inside that cell. If you put cells in a hypertonic solution, water is going to go out to the hypertonic solution, and these plant cells are going to shrivel up. Okay, now there is a word for when they shrink up. It starts with PLA, maybe to help you remember that this big word goes with plants. So it's called plasmolysis. And the reason why it's called plasmolysis is the plasma membrane breaks away from the wall and kind of shrinks in. So that lysis, we're talking about breaking, but it's kind of like the cell membrane breaks away from the wall. So when plant cells shrink, it's called plasmolysis. Let's write that over here. Plasmolysis, okay? Now let's talk about why it's important that we have these full cells of water if we have a plant cell. When water goes in, the pressure builds up. And this pressure is called turgor pressure. Just like if air goes in your tire, we talk about tire pressure, right? If air goes in, your tire pressure goes up. If water goes into plant cells, their turgor pressure goes up. So turgor pressure is a pressure on the wall from the water that's in a plant cell. We don't get turgor pressure in our cells because there's no cell wall. Our cells just break, so we don't get this increase in turgor pressure, which is pressure on the wall. Our cells don't have that wall, okay? If cells, if water goes in and they get high turgor pressure, then these cells are going to be really tight and the plant is going to stand up. Imagine trying to build a tower out of squishy marshmallows. That's going to be difficult to do. Well, when these plant cells lose some turgor pressure, these cells aren't real tight. They're real squishy. And so a plant isn't going to stay upright if its cells have low turgor pressure. So this cell is lacking some water. Some water's come out. That cell has low turgor pressure. Just like if your tire doesn't have enough air in it, it's going to have low tire pressure and your tire is going to be squishy, right? You'll be able to move it and kind of squish it in. So low turgor pressure equals a wilted plant. Okay. We need cells to be nice and tight and full of water. They don't have bones to keep their structure. So that's how they're able to stay upright. If they have cells that are full of water, then you got these tight cells that can stack and keep the plant upright. Okay. So again, low turgor pressure, you're going to have a wilted looking plant.